Welcome back to High Performance Computing. Today we have our second part of our lecture 2, Parallel Programming with MPI. So the first part really was looking into what MPI really is all about. It's called Message Passing Interface. And a little bit, of course, this already alludes to what we're doing. We're passing messages. And we basically looked a little bit why we want to do this. We basically looked in different application domains. We thought about that the application complexity is growing. The more you want to do realism, for instance, in the wave propagation at the coast, you want to have more and more the wave height. Maybe there's a sailing boat, maybe there's a surfer. So basically you have more and more complexity of the real world that you maybe want to simulate. Or you basically at the groundwater modeling, the more you break down basically a big area into smaller pieces and then want to compute the physics between different, let's say, models that we have seen, like the atmosphere or basically the land interaction, and then also the groundwater modeling. Basically, all of this adds to more and more complexity of the application and also more and more data that has to be stored. And in one respect or the other, it could be that the data is so much that a single processor can't bear it anymore. And of course, also when you think about all the complex, let's say, physical formulas that have to be computed to compute the wave height, for instance, this means more and more computing. So maybe one processor is just too slow to compute, especially if you think that we want to do this over a big domain, right? Like the whole coast, or even if you want to have the weather forecast of a whole, basically, country. What could be the benefit of using parallel computing there? Of course, here we break the bigger problem into smaller pieces. This bounds us nicely to the next lecture, lecture 3, that is coming up with domain decomposition, a loaded topic, because it could be also load imbalancing, then how you match this with processors available and so on. We will talk about this in parallelization fundamentals a little bit more. And we learned that basically this MPI gives us a little bit a set of functions that we can nicely use to basically do distributed programming, distributed memory programming, really, because the data is hidden, unfortunately, in the processor memory of the other processor. Hence, I cannot directly access it. It is not a shared address space. Hence, we have to send messages to get basically the data that is basically available in another processor. And we will look into this more and more, why this is useful, leading up also to ghost layers, halo layers, where you explicitly would put before one time step also data in. This is not all at all clear, but we have learned a little bit already in the first part also the idea of a time step and the loops that is basically there to simulate a domain over time and over space. So this is, of course, something which is very important for us in the simulation sciences, but we also learned that actually the data sciences have a complete different approach there. The data is basically governing the idea of the complexity, not really the physical formulas, but also there, let's say, clustering human brain cortical layers, as we had as one example, could be quite a challenging endeavor. So for this, to conclude the summary of the first part, maybe a bit, is then the idea that using MPI has a sort of standardized set of functions. We have seen the send and receive for an example, but also a couple of collective operations, a broadcast, a gather, a scatter. We will learn this a bit more when I do the practical lecture 2.1 with real demonstrations, or you work on it on your assignment. But the beauty in these operations is really the portability. So you can say that almost all, if not all, HPC applications in the world will have the possibility to execute MPI implementations. And with this, they have probably different MPI implementations of this standard available, but chances are that you can still use basically your MPI application and it work when you compile it more or less quite neatly. Still here and there might be practical examples where you have to massage a bit the code, but overall it will work quite nice, which brings us into the idea of this portability. And the reason that this could have is, of course, that you want to have better performance, a better HPC machine, maybe a newer HPC machine with better CPUs, better execution, fast execution, which then also motivate the idea of why we want to do porting of these applications. So in one respect, this is really the first time we talk about parallelism. So for some of you, it might be still a little bit misleading, a little bit too complex to think that instead of the serial programming that we do, often in Java, when we have a certain program that we want to compute, everything is happening, let's say, with one stream of execution, and I can follow it, I can debug it nicely and see what happens. This function is called, that function is called. And now suddenly we have 5 or 10 or 100 processes executing the same application at once. So immediately this adds complexity. So we cannot simply debug that anymore, right? There needs to be distributed debuggers. Also the parallel programming concept that, of course, they exchange messages means we need some synchronization. You remember the ball analogy. So when I send something, the processor that is actually receiving the ball should be ready to receive. Otherwise, the ball will land in the face and will not have an impact other than bleeding noses. In this sense, parallel programming is quite tough. It's much more complex than the normal way how you do serial programming. Hence, we will dive a bit more now into some parallel programming basics to understand it a bit more from different perspectives. MPI will be with us for a couple of lectures now, as is really the de facto standard for programming. But of course, you have also to think about more broadly, thinking in parallel more and more, how you actually do this. And I think the best way how to do this is really doing a practical example, how you come from code then to execution. And we do, of course, very simple programming here in the course. Think about that this should be preparing you, of course, and however, understanding larger applications like the Nest code we were saying, or Parflow for groundwater modeling, others which are running MPI. Once you understand the basic concepts very well, chances are that you have also a good chance to understand the complex applications very well. Of course, we also learned a little bit the domain complexity will be always challenging. That's why often computer scientists and HPC experts team up with scientific experts, with engineering experts to really create meaningful simulations or meaningful parallel applications. When it comes now to the practice, you know the game already a little bit from the last couple of lectures we had. So we had the access to the cluster machine that you should start firstly think about when you think about MPI. And the first thing you really think is what MPI is actually available. Is it Parastation MPI? Is it Open MPI? There are different MPI implementations of the standard available. And you know already how to do this, maybe with module avail, maybe dive deeper with module spider in one of them. And I have to say also, of course, what we need there is to have the access to the system. So needless to say, what we had in the last practical lecture with the SSH standards to access these remote HPC machines is key as well. Here in the course, we do a little bit this open source, high performance computing, open MPI implementation. Although different implementations exist, we on Jötunn stick a little bit to this standard. But once you understand this standard a little bit with the assignments, with the next couple of practical lectures, you will also understand other implementations because they follow more or less the same standard, of course. So the step first then is really when we now extend our examples that we had in the past, still the same. So of course, for us, nothing changed. The first step, we want to have an SSH, basically logging into the remote system like Jötunn. So I do the same for a parallel application. No surprises there. Just for you as a practical idea, of course, now think about that no matter where you go with this SSH, is it the deep system, which is in Jülich in Germany, or is it the Jötunn system in Iceland? Both basically have an MPI, but the question is still, do they have the same MPI implementation? But in one respect, again, this maybe doesn't matter so much because we know that MPI is very much portable, at least to some respect. We also will make our way, hopefully soon, to Jötunn, actually also to look at this system and then basically meet some of the experts that are also the administrators to get a more bigger feeling. What is actually the HPC machine all about? So step 2 then is interesting because we sort of always start with a normal C program if you now basically start from scratch with a parallel application. So the interesting thing here is to take away that, of course, today you would say still many have already very much libraries where MPI is already fully implemented in several different domains. There are libraries which we will also talk about in the later parts of this course, in the CFD domain, for instance. But let's assume we want to start very much from scratch with the hello world, which is absolutely not a parallel program so far, right? This is important. So it's a simple C program. There's no parallelization. We have a main function that just gives out hello world. So very much hard. No, not really. And it gives us then, of course, then the return value, which I said is basically 0 or 1, the exit code, determining if the kind of computation was good or bad. But the key message here is really it's a typical C program, a valid C program. We have used this in our practical lecture the last time, used a C compiler to compile this. And that's what I also tried to already start up. We used a specific compiler to do the transition now to the parallel computing world a bit more easier. And this brings us to the idea of really start more and more thinking in parallel. So this is something which we call an approach called single program, multiple data. And with this SPMD, which is also a sort of very important part, how you really parallelize. And you see it's always different processors, but the same program. So we need later this differentiation mechanism to see which processor I am in the big picture, which brings us in MPI to the ranks to really identify the different processors. But from the 10,000 feet perspective, everybody is executing the same program, but probably always with multiple data parts in the different parts what they're doing. So in this, the parallel processing approach is then really the idea that I also know that I have many other team members, so to speak, tackling this program or tackling this application, this domain, this physics, whatever the application is about. And this brings us to the data exchange. So once I know I have a neighbor that is basically covering the other domain, the send and receive messages comes into the idea. So let's think about the rain forecast or the weather forecast, the wind, when you have, let's say, this blocky cut down of the world that I just have explained to you in the wave propagation. You can imagine that my neighborhood block will influence me with the wind somehow. I don't know how. This will be computed then with the physics, but I need some input data. How much was the wind speed perhaps on the other part to see how the wind speed affect my part. So we more and more come to the idea that data exchange is, so to say, one of the key principles of this message passing. Otherwise, I wouldn't do it, right? The MPI message passing stands for something, and that means usually you want to exchange lots of data. And this data is loaded, could be physical variables, could be parameter values, could be objects. There are lots of different parts and pieces that actually change from one processor to another. Could be the wave height, as we see with the wave propagation over an ocean. This is sometimes even very simple. Could be just weight height, could be a couple of other parameters. So it's not necessarily extremely complex structures. But then also when you think about more particle interactions, maybe in astrophysics, so think about the interaction of planets with a black hole, which is simulated. There, of course, we talk about complex structures with lots of different, let's say, capabilities on the one hand, and maybe also with, basically object variables that really constitute the object status at that point in time, and that we influence with the physical formulas over basically all the time and all the iterations we do. So let's start slowly with the idea that we basically now have to think about, we have the C program, it's very serial, so I need to add something to make it parallel and to make the C program available, that actually you're not only the only one that is executing this, there are many other processors. And this is what we would say is a basic building block now we add to the MPI part, to really bring the parallelism in the game and to also control it. That's what we want. We want to program it. So we start with the idea of maybe editing this file that you already know from the previous lectures with something we call this rank and size. And all what you see now basically will be a little bit also demonstrated actually in the next practical lecture 2.1. But it's already important to understand now that basically the C program, we basically extend more and more. And although this is just the rank and size now, it's a typical C program still. We didn't add much of MPI yet. These are two important elements, which I would say even 99% of all the MPI applications have in one respect or another, maybe renamed, where we talk about the rank and the size of the overall number of processors that are in the game, and the rank, the role that I play in this big game. But still, we need to compile it and to work on it. But this is something what you usually would add the rank and the size information. This is just a normal integer, so we not at all have actually here any MPI in the game. But the interesting thing is now with the MPI header that we add usually in the C programs, we get now the full flavor of all the functions that is available in MPI. And the first thing you want to do is basically create this parallel region. It's basically the idea that between MPI Init and between MPI Finalize, these two building blocks, which are very important building blocks, there is a parallelism happening. Before this, where rank and size now are basically there, there's no parallelism yet. So these are just, definitions of some variables. But as soon as I do the init and the finalize, here's now where the parallelism can start. And we see here MPI init with some basically parameters that you can have as some, let's say, parameters to steer the MPI environment, and then the finalize it. It's an extended simple C program and is basically not really anymore a pure C program, because you need the MPI header and we need to program it in a way that it's then also in parallel. So we would add the printf statement here, hello world, not anymore alone, but also I am someone out of someone, and these variables will be followed and filled during the runtime by rank and size information. Hence, now that is quite an interesting part. We have to say that in a way we want to understand that rank will be very different between each of the executions on each of the processors, and size will be probably always the same, right? So when I have 4 processors executing this, rank will be from 0, 1, 2, 3, up to the size basically, which is then 4. And I would say I'm 0 out of 4, I'm 2 out of 4, etc. Now, here is still something missing in a way. So how we fill rank and size, right? And this is something where the MPI standard gives us now the connection to the communicator setup. And this is a bit important to understand, because as I was alluding to in the first part of this lecture today, this can be defined by us, right? There is a predefined one communicator that we call MPI world, which is a world of all the ranks, all the processors part of the game. So when I use MPI world, I can get the size of all the processors, which we have here basically available. And then the interesting thing is I can get with MPI rank the unique identity of my own processor running within the size, which alluding now to this 0, 5, 7, 6, 1. There's a unique identity in the overall MPI world so that one processor can differentiate the other one. Now, this communicator world is just a predefined one. I have the power later, and I'll show you in one of the subsequent lectures, to create my own groups out of this. So, and then I can have different ranks and different sizes of the communicators, obviously. And this should be also noted here that, of course, rank and size is a variable that lives, so to speak, in the space of this particular communicator that we define and use, which is the MPI world here, but could be also group 1, group 2, derived basically from this com1 and com2. And then you can do the communications within these communicators. But this is also something we want to do down the road. But if you think now that there's a rank and size information integer, we have a parallel part where now the real parallelization setup happens from MPI with MPIRun. And then I have really the opportunity to really initialize rank and size to the proper environment I have in a very specific communicator. So this is now, if you want, a real first proper version of an MPI program that is actually also a proper C program, But the interesting thing is with this information we get from the MPI environment, right? We don't define this. MPI takes care of all of this. We are now able to say hello world out of this processor, out of so many processes. And this is quite interesting if you think about that you not at all implement the low-level details. You're not going in a loop and say, hey, how many processes I really have for a problem? Or when you think about, I assign now everyone a unique ID. I get all of that from the MPI environment. And this is, of course, how we leverage it, which is, let's say, one of the key basic building blocks of MPI, really. You hardly find an MPI program without MPI com-size or com-rank in the definitive idea in these communicators using those. So that is probably pretty much a standard to using this, including, of course, MPI Init and Finalize. So this is something which you should know by heart a little bit, because it's very important to understand this. Now, when it comes to the execution, much of that you already know. So basically now we said the last time we need to load the right modules, right? So in other words, when we want to compute this now and execute this, we probably want to understand and first access, having access with SSH is granted. Then I know, of course, I have it somewhere in a proper directory. I told you also, it's always good to have maybe another directory. So we extend the hello directory with hello MPI and look at this hello C program, which is now nicely extended to hello MPI with the init, with the finalize, with the com-size ranks, which are then used actually even in the output to understand what or who of the which of the processes really has executed this part. It's a bit dry now. It will materialize more when I do the practical lecture 2.1. But as we go parallel, it's good to do different small baby steps to really understand how we move now from serial to parallel. But in the end, and this is now the interesting part, you still have one application, right? We not really do anything specific in parallel. I mean, the only parallel part you would say, what we really influence ourselves was that we want to know something about the parallel region, like rank and size information. We added these basic statements, but we still are basically executing one application only. And this is now the key to understand why MPI works well, why it can scale up no matter how much processes I give it. I can define it, how many basically hellos I'm now getting to this application. You see, nobody says it should be 4, 8, 16 here in the source code. And this is the beauty of this MPI standard in part and how we program without any specific number of cores necessarily in mind, right? It could be 4, the program could be executed on 8. All what is necessary that the MPI environment knows, of course, that I have 8 processors available, 8 cores, for instance, with 8 ranks. But I don't really program the application towards this. This gets more and more difficult the more you dive into the domains, obviously. You have to do domain decomposition, so then you have to think a little bit more about careful what would be the number of processes maybe I assign to different regions, to different domain decompositions, and so on. But here the first step is pretty straightforward and easy. I need to compile it. And of course, for this, we have already discussed the module environment. It's key to understand this with module avail. See that the compilers are there that we had the last time where we used module load GNU and then the open MPI, because basically if we spider open MPI, we know it needs GNU and so on and so on. It could be also different when you think about that you want to use Fortran, for instance, right? So, and of course, the source code now is invalid. It's a C program, so it wouldn't work. But if you have a Fortran code, then you need Fortran compilers. And the one that we used so far, also to motivate a little bit, was the MPI-CC, basically the compiler that is then MPI aware, and we can steer the output here with a -O. If you remember for ping pong here as an example, if I have a ping pong C source code, I can also basically alluding here to having an executable out of this, which is a ping pong. And this is now really a parallel program when you have used MPI directives. Before, it's just more or less a normal C program, right? And this is something to understand. It all fits together like the same way we did before. load the right modules that we need for the compilation. Here, let's say module load GNU OpenMPI is already enough because it has OpenMPI loaded, which then also will understand basically the directives that we had the last time. This is hello C program, which was just a valid C program. Now, what is new now is we have this MPI directives, right? So let's say as we executed this the last time, we said hello C, we ended up with the MPI to have this hello executable, which is this fellow, and we executed it. But there were no MPI statements, so all was good, no parallel programming happening. What's now happening is when we want to go parallel, basically we have this MPIRun environment. It was already in our batch script, if you remember a little bit. Then basically we can steer now the parallel execution of how many cores there should be involved. The number of cores will be in the job script. And so this is dynamically defined independently from the application code, once again. So I've defined in the job script basically the number of processors I want, let's say 4 here, and this is independent from the MPI application that I program, right? So I can steer 8 in the job script, and this hello application would be executed on 8 processes. If I have 2, it would be just 2. If I have 16, it would be 16. And the MPI application hello would be exactly the same on all of them. And this shows you a little bit the power now of scaling up those basically API applications. You program them a little bit without having the concrete set of processor numbers in mind. And the job script is now the integral part that works together with MPI through this MPIRun, for instance, that then distributes also. That's not what we talked before. Of course, when you have now compiled it on the login node, the hello C program, which is the executable, you also have to see how that is now basically together with the scheduler distributed on the kind of compute nodes where you really want to run this application. Let's say 4 different versions in compute 2.0, 2.1, 2.2, 2.3 of Jötunn, for instance. On the other hand, we know everyone should be still aware that I'm a single being, so to speak, and have its own identity. You see here with 3, 0, 2, 1 out of 4. All of them are 4, but this is this rank information we're talking about, which is now the output here that says, well, really, I'm just 1 out of these 4, and I'm aware that I'm also just 1 out of 4. And MPIRun, together with the scheduler, will actually making space for this particular part of this application. And this is definitively where the batch system helps. Hence, one of the next steps in this is really to think about not only defining then this particular application that I want to basically run now on the compute nodes in parallel. Also, I should specify, and this is this part, the number of cores available. And this fellow is loaded. We will see in subsequent lecture that you can steer that much more. But let's assume the simplest way here now is 4 cores available. We have hello, basically this executable now executing the very same executable on all of these different processors. The only difference really is basically the rank is filled with a unique identity given the MPI environment that everybody knows that I'm a 3, 0, 2, and 1 out of the 4. And this is the rank information and the communicator size, which was this com world, everyone. And this is something what MPI gives us in combination now with the job script scheduling this. And the scheduler will make sure at some point in time there will be 4 cores available to run this job. If there's no capacity for the 4 cores, the job wouldn't be executed, right? So this is also something which, of course, when you now specify, let's say 200 on Jötunn, you will see maybe we have not enough resources for that, so it will be never executed. Or another way where you say N4 would be normally possible, but before 1 day of the deadline of the assignment, everybody's using Jötunn right now. So basically you're scheduled to a certain time in the future when this 4 cores become available, again, according to the scheduling policies we discussed before. That's how it a little bit plays together. So in step 6, really all the steps we have learned so far today and basically all the couple of lectures before come now a little bit together with this SBatch idea that instead of having this one hello that we had the last time, we want to have it 4 times. And given I have an MPI application, I'm also aware that it's in parallel executed 4 times. You see that here a little bit, we have this kind of cluster. Maybe the green nodes are still free, but this one uses 4 cores in a simplified, visualization here, occupying 4 cores, and it also knows the application that I'm rank 0, 1, 2, and 3. So I'm aware that there's 4 at the same time executed. And this is what the MPI environment gives us. And of course, needless to say, when you execute this job, there will be still the same concept that the batch will give you a specific job ID. You're scheduled according to the current schedule. At some point in time, it will be completed, and then basically writing an output file. But the difference now is that we will have 4 different processors that wrote actually inside this output file, right? You see here 1, 2, 3, 0 out of 4. All the different identities of the rank have been used with the size of the communicator in one of these output files. I will also demonstrate this to you in the next practical lecture, that you have a much more practical way of understanding this, but that's how it really works in the very small scale. However, the basic principles of ranks, of sizes of different communicators, the executable specified or also implemented a bit independent from the number of cores you really want to run on it, is a key ingredient also of high performance computing. And hence it's really shared with different applications, even much more cutting applications than this hello world here that I have as an example. Understanding this from a different perspective is maybe a good idea. Bringing together different pieces we discussed before. So we said there's this interesting element in the beginning, the include files, so the headers and so on, that have basically the declarations of the functions that have access to MPI functions. I would use them to do an initialization of the MPI environment and a finalization, if you remember. And this is really the block, if you want, or the space in between where this parallel program really lives. So there I have suddenly many more processes available. Before the MPI environments, everything will be still serial and after it as well. That's very important to understand. And of course, sending, after you terminated the MPI environment, some send receives with the MPI environment will fail equally if you put that in front, right? Hence here, the MPI environment, the initialization of this, which then is in line with what we get from the job script, for instance, let's say 4 processes is available. This enables us to do then interesting part here with the message passing calls. And why this is basically needed? Because essentially we still need to know the identification of the other processor I want something sent to. You see here essentially processor 1 and processor 2. In order to send some data over the network between these different processors, I need to know what is the identity or the rank of this processor. So to which rank I want to send the data. And of course, this is a sort of system buffer that then will receive the data. And we have learned already, when I have a send, I need basically another process to be ready to receive the data, where then we'll be going over the network to the system buffer and then finally in the receive command that essentially then, of course, should be having some variable space defined, prepared, so that we can store the data coming from process A. And this is only possible because the MPI environment gives us the rank information where we can then address in a point-to-point communication really a precise rank. And of course, in the end, it's just data going over the wire with a system buffer and so on. But with the send and receive taking care of all the message low-level parts, you as a programmer need just to specify which is a processor that should receive what data. So it's, let's say, really abstracting from the low-level details of this message passing, making it very simple for developers. And when we now revisit this, this is what we had before in the first part. It's much more clarified, hopefully, now that this MPI environment enables us to address a specific processor that or process that really should get this new data. But while this processor has already lots of own data, it wants to receive a new one. So you do a send and receive. And of course, every time the matching one should be also in this point-to-point communication really ready to receive. Now, Doing this in practice next time will be the ping pong command. I just want to briefly illustrate this here. And of course, it's a very trivial setup. We have just two processes here involved, where you say, if you rank 0, let's assume this is rank 0, this is rank 1. If you rank 0, then your destination is rank 1. You basically want to then have the idea of saying an MPI send first, basically to processor 1 with a char, whatever it is. Here, the message is basically the X, which we want to have there. But it is the out message here, the X, that we will specify an MPI char to the destination. And we do this in the MPI.com world that we obtained here, the rank from. And this is a ping part. Now, we also said, like, ping alone is not happening. We need processor 2, which is then rank 1, to be ready to receive. Hence, to realize a ping and the fully completed ping that you see here in the first part, we need to have a receive that is basically making space in the buffer and in the memory space for an in message to obtain basically then the X and one char from the source, which is obviously process with rank 0, which is rank 0 sending basically something in the buffer on the in message of processor 2. So this is a ping, while now we want to do a pong, as we said, saying that this rank 1 should then initialize the message exchange, where it's all basically a little bit inverse if you want, where you're saying, of course, now you have the out message you send, one MPI char also in this COM world, and you basically now want to have this to the destination 0, which means, in other words, again, processor 1 with a rank. But we know also the story, this would be not a pong if not the rank 0 here would be basically able to receive it, or ready to receive it. So in order to have the ping, these first lines are important, and then the pong, the second lines are here important. And the interesting thing now, what you get more and more, is the identification of the rank, this unique ability to understand what role do I play in the bigger setup as a rank, enables us to now modify the source code in such respect that each of the processors may be doing something differently, right? That is now the same application, the same C code that you see here, including MPI Init, as we discussed, with Finalize and print something out, what we really was, receiving and getting and so on. But you see this if rank 0, else if rank 1, I'm able to steer the code a little bit differently to realizing then this ping and this pong. This will be much more clear when we dive into the material of practical lecture 2.1. So I think I'll leave it a little bit there in the ping pong, just to shed light also of other public, very powerful parts, which is used a lot in public applications, in a broad set of wider applications. Available really is a broadcast. It's one of the most used perhaps functions, where one processor wants to now send information to all other processors, not just the ping and the pong and so on. So here we're talking about really broadcasting some data to all the other processors. Also, this I will, of course, show you a little bit in practical lecture 2.1. There you, of course, go through essentially the role of 1 that is actually starting all of this. So you would say if rank equals a source here, for example, still the same matters with size and rank information. And then basically do an MPI broadcast to all those processors with MPI.com world. And you see a little bit that you specify the source, but never the destination, because the destination is automatically more or less indirectly defined via the communicator, because it sends the information to all those processors which are part of MPI.com world. So instead of point-to-point communication, there's no need for a destination, just more rather the kind of count of information you want to cross, and of course the kind of data types and so on. And then you basically want to fill the buffer here that is basically initialized. And then if you broadcast it to all the others, we can also see then here how the buffer is filled across all the different processors, because it will be still executed 4 times, but all of them will have a different role in the broadcast operation. the rank will have a very specific role here of kickstarting this, while all others, more or less with broadcast, receive and fill the buffer. Only the rank 0 will initiate the broadcast, more or less in a sense of really sending then, while others are receiving, and then getting the buffer here basically initialized, because here we see if rank 0, it would be not initialized, and then you can basically control that. But I will also show this in practical example as part of the next practical lecture. So when you don't really catch all of that, don't worry. I think the next application parts that I will demonstrate will be helpful. And again, here's an interesting application example. It's a bit more elaborate, using one of these collective operations, serial versus parallel, and so on. So I would recommend you also to look at this particular lecture. And that's really all I wanted to say today for the more conceptual idea of MPI. We will follow suit with a practical lecture on MPI in 2.1. So see you next time.